In our last video, we learned about the Frenet frame. In this video, we're going to learn a cool thing about acceleration. So we know for any particle moving in space, there's a direction of motion, an inward direction given by big N, and then a mutually orthogonal vector, big B, which I can't really draw here because of some choices, but it would be pointing under the board because it's following a right-hand rule from T and N, from T to N. Okay, well, one really neat thing is that the acceleration vector always lies in the plane spanned by T and N. The acceleration vector always lies in the osculating plane. It does not have a component in the direction of B. The fact it lies in the osculating plane means I can write the acceleration vector as a linear combination of T and N. That is, I can write the acceleration vector as some constant, which I could call C times T, and some other constant B times N. These aren't the variables we traditionally use for these constants. I'm going to write those down up here. But this is a really cool fact. And you can actually pause the video here, and there's a video under where this video was linked. There's a PDF linked under where this video was linked in Moodle that actually derives the formula I'm getting ready to show you, thereby proving that I can write acceleration down as a linear combination of T and N, meaning that no matter how my particle's twisting and turning through space, the acceleration vector always lies in the osculating plane. So the more traditional way of writing this down is this constant in front of T we call A sub T. And the one in front of N we call A sub N. And they are the tangential and normal components of acceleration. So, the tangential component of acceleration, if you look through the handout, A sub T is the derivative with respect to time of speed. The acceleration in the direction of motion is the second derivative of some kind of position, right? This is ds dt, right? Take one more derivative. This feels like a Calc 1 problem, right? The derivative of speed gives me acceleration in the direction of motion, in the tangential direction. And then we have the normal component of acceleration. Okay, and we can write down a really sophisticated formula for it, that is the curvature times the square of the speed. And we can make that calculation. That's not too bad. But one thing to always keep in mind, because acceleration just lies in a plane determined by T and N, we could actually look at that plane and then use the Pythagorean theorem instead. The magnitude of the acceleration vector minus the tangential component, take a square root, that will give me my normal component. And sometimes this arithmetic is easier to do. So let's take an example and see if we can calculate the tangential and normal components of acceleration. And then I want to express the acceleration vector in the format listed here, where I'm going to write it down as a vector in terms of big T and big N. I'm not actually going to calculate T or N. I'm going to use these as symbols, right? Because there's a tangential and a normal direction. So for that example, I kind of want to take our favorite example, or my favorite example, that helix we keep looking at. And again, let's let T be bigger than or equal to 0. So we just think about that helix kind of coming out of the xy plane up towards the camera. Well, at this point, we've done this calculation enough, we might remember what the speed is, but just in case, I'll take my derivatives. All right, and then speed would be the square root of sine squared plus cosine squared is 1 plus 1 squared is 2. All right, so speed is constant. And this makes it a really easy calculation. for the tangential component of acceleration. The derivative of that constant is 0. For a particle moving along that helix, it is experiencing no acceleration in the tangential direction. Now, we need to see if we can calculate the acceleration in the normal direction. So I'm going to think about a sub n as being the square root of the magnitude squared of my acceleration vector minus the tangential component of acceleration squared. Well, I know what that is. That's just 0. Okay, well, the square root of a magnitude squared is the magnitude. All of the acceleration is in the normal direction, so I just need to find the magnitude of the acceleration vector. So one more derivative. There's the acceleration vector itself, the magnitude of which is 1. All right, so now I'm ready to write down the normal component of acceleration, a sub n. It's 1. Okay, so now what we can do is we can write the acceleration vector as a linear combination of big T and big N. Okay, well, the acceleration vector is a sub t times the unit tangent vector, big T, plus 1 times big N. There is my acceleration vector written down in that format. I don't need to calculate big T or big N. This is exactly what those instructions mean. One cool thing is if you go through and calculate big T and big N and plug them in and distribute and combine everything, you're just going to get back to the original acceleration vector. Okay, what this means is all of the acceleration is in the normal direction. We're going at a constant speed in the direction of motion, but we're accelerating because we're turning and moving along that helix. None of the acceleration is in the binormal direction. All of it's in the normal direction. And this is that very famous physics problem that I think I've mentioned before. Right? You're taking a physics 1 test, and the question is, you're driving in a car, and the speedometer always says 35 miles an hour. It never changes. Can the acceleration be non-zero? And the answer is yes, because you might be turning, right? You might only have a normal component to acceleration, even though the tangential component is 0. Speed wouldn't change, but you would have a non-zero vector, acceleration vector. To relate it to our helix, maybe we're going up one of those helical parking deck driveways. All right, that's it for now.